Hello, Math 13 students. We have some technical detail for section 6.2, applications of normal distributions. The keystrokes here are going to be almost exactly the same as they were in section 6.1. The only thing that really changes is the mean and the standard deviation. We'll use the normal CDF tool to find probabilities. We'll use the inverse norm tool to work backwards and find scores. So we use both tools in both directions. Let me go ahead and share my screen and we will get going. So, chapter 6.2, applications of normal distributions. All right, so you see there the two tools we're going to use, the normal CDF and the inverse norm tool. We have an outline. We're going to focus on real-world applications in this presentation, and we'll use those two functions I've already mentioned. We'll take a look at appropriate examples as we take our trip through these keystrokes. Here's our first example. Birth weight of newborn babies follows a normal distribution. We have a mean of 3,152 grams and a standard deviation of 693 grams. And we've got a couple of questions. We want to find the probability that a randomly selected baby is heavier than 3,500 grams. And then we want to find, let's see, well, about 1.4% of babies are a very low birth weight. We want to identify the birth weight that defines these two, newborns. So, you can see we've got the two types of questions. We have a question about probability and a question about scores. All right, probability first. We want to find the probability that that little baby is bigger than 3,500 grams. I really think a picture is very, very important here. So that's the piece of real estate I'm looking for. That area will be the probability that a randomly selected baby is heavier than 3,500 grams. So over here, we have the normal CDF. So for the lower limit, we have 3,500. For the upper limit, I'll take 10 and I'll raise it to the 10th power. The mean, 3,152 grams. The standard deviation, 693 grams. We're going to paste that into the normal CDF function. There we go. All right, so the probability that a randomly selected baby is heavier than 3,500 grams, if I round that to 3 significant digits, we have 0.308. So the probability that that little baby is heavier than 3,500 grams, 0.308, or about 3 out of 10 babies are heavier than that amount. All right, that's our first question. Here's the second part. 1.4% of babies are of very low birth weight. We want to identify the birth weight that defines these newborns. All right, so I'll need to provide both the mean and the standard deviation, but I also need to remember that when I go after a score, I need to provide the area measured from the left up to the point of interest. So 1.4% is a 0.014 when I convert that to the decimal format. Over here, the area, 0.014. The mean, 3,152 grams. 693 grams is the standard deviation. Plug that in. And there we go. 1,629 grams of change. Since my statistics are in whole numbers, I'm going to go ahead and round that to a whole number also. So that weight, 1,629 grams, defines the lowest 1.4% of babies. If you're lighter than that, you're a very small baby. Example number 2, we're going to talk about shoes. Women's shoe sizes, normally distributed. We have a mean of 8 and a standard deviation of 1.5 in terms of shoe size. What is the probability that a randomly selected woman has a shoe size smaller than 8.5? The follow-up question, what shoe size defines the top 10% of women's shoes sold? Smaller than 8.5, what is that probability? So there we go. We've got the area identified, and we're ready to reach for our calculator. Lower Let's see, we've got a negative 10 raised to the 10th power. Upper limit, 8.5. The mean, 8.0. Standard deviation, 1.5. Paste that into the probability function. And the 0.631 when I round that to 3 significant digits. So the probability that x is less than 8.5, 0.631. All right. What shoe size defines the top 10% of women's shoes sold? I'll remember that I need to work this question using an area measured from the left. I'm interested in that area on the right, the top 10% of area. So what I'll need to do is I'll need to use the complementary argument. So the area I am interested in is 0.90, or 90% of the area as measured from the left. So back over here. Area, 0.90. Mean, 8. Standard deviation, 1.5. Plug it in, blow on it once for luck. And I get a 9.92 and change. I'll round that to 1 decimal place because my mean and my standard deviation for women's shoe sizes have 1 decimal place. 9.9, that's the shoe size that separates the top 10% of shoe sizes from the rest. All right, now, let me go ahead and wrap this up. We now have focused on real-world applications. We used both the normal CDF and the inverse norm tools to take care of their respective tasks. We introduced appropriate examples. That means I'm done with this, and I'll say goodbye and stop the sharing. All right, goodbye. Go ahead, do some homework, come back and find me with your questions. Thank you.